Okay, so we're going to talk a little bit about overloading. So overloading is something we have seen already in Haskell. For example, when we look at types of certain operators, they work on not just a single type, but a whole family of types. Let's take an example of the multiplication operator. So we can ask, what is the type of the multiplication operator? And you see that it works for any kind of number. As long as something is in the class of numbers, the num class, then this operation can take two of those things and give you back one of those. So that means whenever we define a function that uses this operation, then that function may inherit the overloading that this operation has. For example, if we define the square function, square of some number x to be x multiplied by itself, we can ask what the type of square is, and we see that it inherits the overloading that the multiplication operation has. That is to say, it will work on any kind of number, anything which is in the num class. As a more illustrative example, consider one of the better known functions from the module data.list, namely the sort function. So the sort function will sort a list of things into order, and it can only do that, and it will do that for any list of things where the things themselves are in the ord class. And this is because the sort function inherits the overloading from the comparison operator, namely this one here, the less than or equals to, I would guess, in the definition of sort, which takes any two things in the ord class and compares them, giving back a Boolean result. So what do type classes look like and how do they arise? Well, they're not just predefined things like the classes ord and num that are already defined in the prelude, but there is a syntax for actually defining your own classes. And we can take an example, namely the definition of the predefined num class. So a type class makes a declaration of a type class, looks like this one here. This is the type class declaration for num. And it declares a set of related methods and overloaded functions, operators, and so on, that the members of the class will enjoy. So for example, to be in the num class, you need addition, multiplication, subtraction, unary functions, negation, abs, signum, and something to convert from an integer to a member of that num, to that instance of the num class. So this is the declaration of the signature of the num class. So everything in the num class has all of these operations. And when we want to create an instance of the class, for example, we create some kind of number and we want to add that to the num class. For example, take the standard instances of the num class like int, integer, and so on. We create an instance of the num class with an instance declaration. So we declare that, for example, int is going to be an instance of the num class, so I don't need to translate that to French, where we provide as local definitions to the instance declaration, definitions for the members, for the methods of the class. So just a little note that's in this slide, although there is a clash, sort of similar terminology to things that you will find in object-oriented programming, one has to be a little bit careful here. Type classes here are to do with overloading and not to do with object classes, as in object-oriented languages. So they're more like interfaces. Another example, the EQ class for equality. So here's a declaration of the EQ class. It declares a signature with two methods, equality and inequality, which take two things and give you a bool. And as part of the class definition, there are some default implementations. So the default implementation of not equals is defined in terms of equality, and equality is defined in terms of not equals. So what that means is, whenever we declare an instance of the EQ class, we can provide one or the other of these two definitions, and the other one will be derived automatically, so to speak. So we will fall back on the default implementation whenever we don't provide a definition for equality. And you might consider which types do not support equality. Not all types do, and we have seen some of those. For example, any of the function types don't support equality. They're not in the EQ class. Okay, so something that will be important to us in several of the lectures today will be defining your own instance. And here's an example that shows how that might be done in the case of a simple data type. This is the case of a traffic light, which is one of three values, a red, yellow, or green. Now this is, EQ is one of the classes that can be derived automatically, one of the few classes that can be derived using deriving EQ. But if we imagine now that we didn't actually have the deriving EQ possibility, how would we add this new type to the EQ class? And here's the declaration that could do that. We could declare that there's a new instance of the EQ class, namely traffic light, and in order to define it, we need to define one of the two functions, either equality or inequality. And it's, I guess, usually easiest to define equality. And here's a definition that you could give using pattern matching. Red is equal to red, yellow equal to yellow, green equal to green, and any other pair of colours are not equal. So any other combinations will give you false. And that will be a way of putting traffic light into the EQ class without using deriving. And indeed, we could have a special version. We could choose to define the equality operation any way we like. For example, we might want to have a kind of taxi driver version of equality in which green and yellow are considered equal, which might maybe reflect equality in some worlds. So one more example of an instance declaration, and it's a little bit more elaborate. This is the instance declaration that you would have for equality on pairs. And if you want to test for equality on pairs, you need to be able to test for equality on the components of the pair. So this declaration says if A is in the EQ class and B is in the EQ class, then we can declare a new instance of the EQ class for pairs AB by defining the equality operation for pairs x1, y1 and x2, y2 to be defined to be when both x1 is equal to x2 and y1 is equal to y2. So this may look like a recursive definition in some sense, but it's not recursive. It's just describing how equality on pairs of things can be defined in terms of equality on the components of the pair. So this is not a recursive definition because the equality operation on the right-hand side is being used at a different type. This is a different equality operation than the one being defined on the left-hand side of the equation. However, an instance declaration of this kind will actually introduce infinitely many instances. And a similar case for lists. So when we have, for example, equality on lists, that requires that we have an equality operation on the elements of the list. And that means that these instance declarations correspond to rules for deriving new instance declarations. So for example, if we start off knowing that we have equality on integers, booleans, and so on, then if we apply these rules, then we get equality on, for example, lists of int, or lists of int, and so on, or pairs of int and bool, or lists of pairs of int and bool, and so on. So instance declarations of this kind that have a constraint give rise to infinitely many possible instances. And that's quite a very useful mechanism for defining operations on complex types, as it were, almost automatically. So if you want to know a little bit more about the type classes, the standard classes, and in particular, then I suggest you look at the slides that I'm previewing here. They're from 2018 by Thomas Hallgren, where a number of the standard classes are listed. For example, the enum class for things that can be arranged in order. The enum class is one of the cool ones that has a cool syntax. That's the syntax we see with this dot dot notation. So this is something that is part of the enum class. We can do that with anything in the enum class. For example, characters are also in the enum class, or any types of your own that you choose to add to the enum class. You'll be able to use this kind of syntax to talk about them. Bounded class as well, therefore, classes which are which have min and max bounds. So examples of that would be bool, char, and int, but not integer, because there are no minimum integers and maximum integers, but there are a min and minimum value for the int and maximum. And the show and the read class. And the show class, there's a bunch of things, both in the show and read class, but I think what's important here is that in the show class, there is a function called show for converting things in that class into strings. And that's something we might use. We might declare an instance of the show class when the string that we want to display is not the one that we might derive using a deriving clause. If we want to have something else. For example, if we wanted to display a playing card in a nicer way, then we might declare our own instance of the show class. And just to summarize derived instances, there are a whole bunch of them, but not so many. In fact, these are all of them. EQ, odd, show, read, enum, and bounded are the ones that can be automatically derived. And here's an example of how you might declare your own show instance. For example, we might declare a show function for suit, which instead of printing the word spades actually prints the Unicode character corresponding to spades, because Haskell supports Unicode characters, and these are valid Unicode characters. Okay, as I say, there's a little bit more about this in the slides, and I won't go through them more on this in this recording. So the reason that we are talking about overloading at this point is because we are going to need that when we look at today's main topic, which is test data generators. So test data generators are the programs that instruct quick check on how to generate random values. And these are a form of instructions similar to the I/O instructions that we saw last week. Now the connection with type classes here is that quick check can perform random testing on any values that are members of a class called arbitrary with a big A. So if a type T is in arbitrary, many types we've seen are in arbitrary, for example, int and integers and lists of such, then there is a random value generator that quick check will use internally to do its random testing. And the name of that generator is called arbitrary with a little a. And that has a type called gen T, if T is the type we're interested in. So if we're interested in generating arbitrary integers, then arbitrary in that case will have a type gen integer. So gen integer should be read as quick check instructions for generating an integer. So today we're going to see how we can program with these things. And in doing so, we're going to see an interesting link to the topic of last week, the last lecture, which was I/O.